Now we know who's who. Richard will tell us more about on the multiplicity one conjecture for mean curvature flow.
All right, yeah. Thank you for the opportunity to let me speak here, and thank you to the organizer to organize this nice conference. Happy birthday to you, Tian. Today in this talk, I want to continue where Bruce left off. So I want to state the results that we obtain more precisely, and then also give you a little bit of a sense how we go about to prove those. Okay. So let me first recap a bit. So maybe using slightly different symbols here. So recall again, we have, let's say we have some mean curvature flow, which I'll denote by a script mt. And we want to understand its singularity formation at the singular time t. Then to do this, we can zoom into the flow and we can take a pointed sequence of blowups. So we rescale distances by a factor of lambda times by a factor of lambda squared. And when we do this, then it was shown by Ilmanen that these flows weakly, in some kind of measure sense, converge to a shrinker, which we can then analyze more carefully. But the caveat here is that this shrinker may occur with higher multiplicity, and this convergence is also not smooth. Okay? And so this then leads naturally to his multiplicity one conjecture, which says that the multiplicity of this limit should be 1, and hence this convergence should actually be smooth, just smooth convergence, like nothing very specific. Okay? And so, as Bruce has already stated, so we prove that this multiplicity one conjecture is true. And in particular, sorry, this implies that the convergence is indeed smooth. So we're smoothly converging to the limiting singularity model. And in fact, any blow-up limit, not just blow-up limits where we fix the base point, it has multiplicity 1 and the convergence is smooth. So whenever we see some mean curvature flow and we zoom into the mean curvature flow, however we do this, we're going to see some limit after passing to a subsequence, and that limit is just multiplicity 1, and we're converging to the limit smoothly locally. And so one particular consequence of this is, for example, that a minimal surface cannot occur as a blow-up limit of mean curvature flow. So we just don't see higher multiplicity in any sense. And then our theory has some a nice byproduct, which is that there is a pretty elementary notion, which we call almost regular mean curvature flow, which somehow covers all the interesting cases of mean curvature flows through singularity. So this is what Bruce has alluded to in the previous talk, that we still need to fix a good notion of mean curve of flowing through singularities. And there were certain candidates for doing this, such as level set flows or Brachy flows. But we somehow came up with this new notion, which more or less covers all the cases that people are interested in. And it's somehow a surprisingly simple notion. So it just says, that we just define a weak mean curvature flow flowing through singularities as some object which is somehow smooth almost everywhere. So it can be described by just the mean curvature flow PDE. And then there's some singular set, but the singular set is somehow small enough so that we can carry out all the necessary integration by parts. Okay? So it's and so this notion also then, we also have a nice existence theory within this class of these flows, and in some cases, even a uniqueness theory. All right, so now let me talk about the applications of this result. So as Bruce mentioned in the previous talk, there are several conjectures in the field of mean curvature flow, and there has been some excellent work, especially in the last 10 years, trying to address these conjectures, but they often ended up being conditioned on the multiplicity one conjecture. So what I'm going to do now is I'm going to remove this assumption of the multiplicity one conjecture, and then I'm going to take credit for every single conjecture. Okay. So so let me now just set the stage here. So I assume that M is an almost regular mean curvature flow. So in some sense, some mean curvature flow that flows through singularities. And then I'm going to define what we call the generic singular time. And this will make sense in a moment. So the generic singular time is somehow the last time up until which all singularities are described by either cylindrical neck pinches or spheres that become extinct. Okay? So these are kind of the nice singularities, the ones that we somehow understand pretty well, and the ones that we know will have to show up anyway. Okay? So then here is the first corollary, which is based on work by Choi, Hasselhofer, Hershkovitz, and White, and several combinations, which is that the flow restricted to the interval, the time interval up until the first generic singular, time t-gen, is uniquely determined by the initial time slice. And if that time is finite, so if we see some non-cylindrical singularity, then there has to be a non-spherical or non-cylindrical tangent flow of multiplicity 1 at that time. Okay? So up until the time where we see some non-cylindrical flow, tangent flow, our flow is uniquely determined and flows through singularities in a unique way. Then the second result is based on work by Brendle, who classified shrinkers of genus 0. And well, if we have if we know that all the tangent flows have genus 0 and therefore are cylinders or spheres, then this time t-gen just has to be infinite. So if we start with the two-sphere and evolve this two-sphere by the mean curvature flow, then we may hit some cylindrical or spherical singularities, but these are all the singularities, and the flow is uniquely determined by the first result by the initial condition. So this is somehow an interesting case where we can show that under this topological assumption of the initial condition being a two-sphere, this kind of mean curvature flow PDE becomes well posed within this class of these almost regular mean curvature flows. If we go higher in the genus, then the PDE is not well posed anymore. And then corollary 3 is based on work of Chodos, Choi, Montolidis, and Schulze, which says that if we start with some initial condition, some closed surface, then well, we may hit some non-cylindrical singularity, but if we don't want this, then we can just slightly perturb the initial data to choose some more generic flow, and this generic flow will then only have cylindrical or spherical singularities. Okay? So again, they've proved this corollary with the additional assumption of the multiplicity one conjecture, and this is what we can remove now. Okay. Let's see, are there any questions so far? Yeah. Mm-hmm.
About the sphere shrunk in time for finite time.
So yeah, good point. If the flow is empty, then I assume it exists for all times. Yeah, it may be empty. Yeah. Okay. That's my convention. Any other questions? All right. So the next corollary is more about the structure of these almost regular flows when we maybe don't have uniqueness. And to do this, I have to digress briefly to give you a little more context. Okay? And some of this was also already mentioned in Bruce's talk, so I'll be a bit quicker. So first of all, recall that we have the avoidance principle for mean curvature flow, meaning that if we have two embedded surfaces that evolve by mean curvature flow, if they're disjoint at one time, then they remain disjoint. So this is the avoidance principle. So now let me use this avoidance principle to characterize kind of weak mean curvature flows. So to do this, I'm going to now change my picture from thinking of mean curvature flows as a family of embedded surfaces and instead look at their space-time track. Okay? So I'm thinking of a mean curvature flow now as just a subset in space-time, just the space-time track. And then I'm going to define a weak set flow as a closed subset that just satisfies the avoidance principle for any other smooth mean curvature flow. So this is a viscosity way, like a viscosity method of characterizing mean curvature flows in a weak way. So and then if you sit down for a moment, you notice that this definition does not somehow characterize flows uniquely. So for example, you could start with some initial condition and then just choose the empty set. It certainly satisfies avoidance because there's nothing to avoid, but it's certainly not what we want. Okay? So to get around this, what we can do is we can define, we can look at the maximal set, which is a weak set flow. And this is then called either a maximal weak set flow or a level set flow. And there has been a lot of research on these flows. And again, if you sit down for a moment, you'll see that for every initial condition, there's a unique weak set flow starting from this initial condition. It doesn't even have to be a surface, just has to, unique level set flow or maximal weak set flow, thanks, yeah. It doesn't, you don't even have to start with a surface, you can just start with any subset and you get this maximal weak set flow. However, even if the initial condition, so if the initial condition is smooth, then this weak set flow will agree with the evolution of the mean curvature flow for as long as the flow is smooth. But at the first time that the smooth mean curvature flow hits singularity, the weak set flow may do something very uncontrolled. And I'll show you this in a moment. And so this is due to a result of Brian White. So beyond kind of the first singular time of the smooth flow, the level set flow may evolve and may show this phenomenon called fattening, which is also associated to non-uniqueness. I'll show you this in a moment. So how do we get around this? So one normal setup is to write down what we call these canonical flows starting from a smooth initial data. So I'll do the following. I'll start with some smooth embedded surface in R3, and I'm going to look at the two sets K plus, which is the subset that's contained, that is bounded by M, the compact subset bounded by M, and K minus some of the outer subset, the blue subset. And then I can look at 5 interesting weak set flows. So the first weak set flow should be, the first 2 weak set flows should just be the level set flows, so the maximal weak set flows starting either from the red part or the blue part. Okay? The outside set I can evolve it by the level set flow or the inside set. I can also evolve M, the surface, by the weak set, by the level set flow. Okay? And then I can also look at the boundary of these 2 weak set flow, the outer and the inner weak set flow. That's a weak set flow, not a maximal one, but it's also a weak set flow. Okay, so the advantage of the first 3 weak set flows is that they are level set flows. They're maximal, but the disadvantage is that we don't know whether they're 2-dimensional. Okay? And so the advantage of this flow is that we know it's 2-dimensional. It's the boundary of something, but we may see some non-uniqueness, which we can characterize as follows. So suppose that we're evolving this picture in time. So then the inner set will evolve and the outer set will evolve. And the set in between will, M of t, the level set flow starting from M, will separate these 2 sets up until we hit the first singular time or some singular time. And now what could happen is that the outer flow may be the outer flow is somewhat, the blue flow may be overlapping with the red flow in a set of non-zero measure. So it may look like this. So the evolution of the outer flow, the blue set flow, may now be the combination of the blue subset and the purple set, and the evolution of the red set may now be the union of the red set and the purple set. And then the evolution of the black line, so the surface separating these sets, may now be the purple subset. So the purple set fattens, and we see now it separates some of these 2 flows, M plus and M minus, from one another. Okay, so here we see that these flows are non-unique. This is a non-uniqueness phenomenon. Okay, so the inner flow and the outer, so these boundaries here of the purple set are called the outermost flow or the innermost flow, because they somehow characterize the outermost version of the flow or the innermost version of the flow once we incur this non-uniqueness. All right, so now what we can now do is we can use our result to characterize these outer and innermost flows. So we can show that there is a time t fat, the fattening time, where the boundary surface fattens up, such that for times before the fattening time, we see a picture like over here. We have the surface separating the outer and the innermost flow has measure 0, and the 2 flows, the outermost flow and the innermost flow, agree. And then past the fattening time, or at least sufficiently close to the fattening time, the surface MT will have non-empty interior, and then also will separate the outermost flow from the innermost flow. Then they end up being different from one another. And the flow M is uniquely determined up until the fattening time, which is always occurs after the time Tgen. Okay? Because fattening can only occur if we have a non-cylindrical or non-spherical singularity. So now what are these? A priori, these outermost and innermost flows are still weak set flows, but we can now also say that these flows have, we can say something about the regularity of these flows. So we can now show that these outermost and innermost flows are almost regular, so meaning that they're smooth for almost every time t. And in particular, the singular set is one-dimensional. And except at finitely many points, basically where the genus drops, these are the ones, the tangent flows are spheres or cylinders. Okay? So these outermost or innermost flows, they just look like these standard, like almost these standard flows which only have these neck pinches, but then there are these finitely many points where we may see a tangent flow which is not cylindrical, and this is exactly where the genus drops, but then the flow continues just looking like a flow with spherical and cylindrical singularities. All right, so this is the characterization that we can give here. Maybe before I continue, let me see, are there any questions? Okay, so now let me try to give you a few details on like somehow the proof of this multiplicity one conjecture. So again, here's the multiplicity one conjecture. Before going into the proof, let me just show you two potential counterexamples. Okay, so something that we should worry about when we try to prove this conjecture. So the first potential counterexample is as follows. So take a minimal surface, for example, a catenoid. Okay, so now if you evolve this catenoid by the mean curvature flow, then it will just be constant. You certainly don't have higher multiplicity. But now slightly perturb this catenoid. Okay, so it's not a minimal surface anymore, so it will change shape under the mean curvature flow. And let's suppose that maybe this minimal surface is stable or something like this. Okay? So the flow will probably try to take this perturbed surface back to a minimal surface, and the perturbations will kind of die down maybe exponentially. Okay? So, however, we may not converge to this catenoid, but maybe to the catenoid of half the size. Okay? So these perturbations, they die down, and maybe after an hour, we converge back to almost a minimal surface with much smaller perturbation, but the catenoid has half the scale. So this took us an hour, but now we still don't have a precise catenoid. We have something which is a perturbation of a catenoid, and now we're at scale 1/2. So everything that we're doing now will happen faster. So maybe after another half an hour, we see a perturbation of a catenoid of smaller scale, and so on. So we have a geometric series of times, and the catenoid will just keep shrinking and limit to a multiplicity 2 plane. Okay, so we have this kind of weak, essentially this null mode in the linearization, which can cause problems. So here the limit is a higher multiplicity plane. Now, let me show you another counterexample, which is the one where our proof is mainly based on, which is more of a compact counterexample. So in this example, sorry, I couldn't draw the 3-dimensional picture here. So instead, let me draw something 2-dimensional and then just think about the rotationally symmetric picture. So I try to draw the axis here and take this blue curve and try to rotate the blue curve around the axis. So you get a rotationally symmetric 2-dimensional surface. And well, what you get is basically something that looks like 2 concentric spheres. They're very close to one another. And this region here, when you rotate it, it gives you something that looks like a catenoid, a small catenoid. Okay? So you basically see these 2 concentric spheres that are connected by this small catenoid. Well, if you evolve 2 concentric spheres under the mean curvature flow, then one of the spheres will just pinch pinch down to 0 earlier than the other one. So you certainly don't have to worry about higher multiplicity. Kind of the distance between them keeps increasing. But if they're connected by a catenoid, then what could happen is that this catenoid will try to push these two surfaces together and will somehow try to kind of reduce the distances between them. And then what could happen is that in the limit, we can see a double density shrinking sphere. Okay? And so this is some of the thing we need to worry about here. Okay? And even worse, as some of these sheets get closer to one another, the catenoid could become smaller and smaller, and then kind of zip around in the sphere and kind of exert even more force at these two sheets. All right. Okay, so now these are the two potential counterexamples. So maybe let me see, are there any questions? Since we have some time. Okay, so now let me now tell you how we can address these potential counterexamples, and I'll get back to this picture in a moment. Okay? So first of all, let me mention two ingredients that will go into the proof, the two main ingredients. And to do this, let me again recall this idea of the Gaussian area. So again, let me suppose that we have a mean curvature flow, and let's just, for simplicity, assume that it exists for negative times and that it has a singularity at the origin at time 0. Okay? So we can look at blowups, and the blowups will look like this. So we look at blowups, and let's say maybe we see some higher multiplicity when we blow up. Then we can write down the ambient Gaussian, which was already introduced in Bruce's talk. So this is the backwards Gaussian in the ambient space. And we can compute the Gaussian area, where we just integrate the ambient Gaussian over the corresponding time slice. And so this was due to a result of Huisken. It was shown that this Gaussian area is monotone. So it increases as we go further backwards in time. So tau is is the time parameter that goes back, parameterizes backwards time. And the derivative of the Gaussian area is this integral here. Okay? So this is a famous formula, but it's in some sense a global formula. It involves integrals. Okay? And so what you can do now with this global formula is you can ask what's the corresponding local formula. Okay? And the corresponding local formula is this. So the local formula says that if we apply the conjugate heat operator to this Gaussian, so this is the conjugate heat operator on the surface, where the time derivative somehow should move with the surface, then this is equal to this term in the integral. So this is the corresponding local formula. Okay, so this is certainly something that's probably been known to people in mean curvature flow, but it's a crucial formula. Okay? So the idea, the reason why these formulas are related is if you take this formula and if you integrate it over the surface, then you get this formula back. Okay, so somehow the Laplacian goes away and the time derivative, and the h squared just gives you the distortion of the area element. Okay, so this is somehow a sub-solution to the conjugate heat equation, or super solution, however you want to view it. Okay, so this is ingredient number 1. And then the next ingredient is a new function that we came up with, which we call the separation function. And the definition is relatively easy. So suppose you have some time slice of a mean curvature flow. So I'll just draw a one-dimensional picture, but you can think of a two-dimensional surface. So, and take a point x on the surface. So now what I'm going to look at is I'm going to look at the maximal ball, or the maximal R ball, where such that the intersection of the R ball with the surface is still connected. Okay, so it's essentially just the distance to the nearby sheet. Okay, or maybe you can say it's the minimal one, the infimum over all radii, such that this intersection is not connected. Okay, but you're just essentially measuring the distance to the other sheet. And this is called the separation function, and I'll call it S. And so now we're going to call a point x good if all the smaller spheres intersect MT transversely for all smaller radii. Okay? So if you somehow try to draw a few of these pictures, you'll see that there could be cases where somehow the surface somehow starts to bend around kind of near the sphere, and kind of you're not measuring the distance to the nearby sheet, but you're kind of measuring where the surface deviates. So we don't want to see this. This is a bad picture. We're really just interested in kind of the component that contains X should be more or less flat, and then there should be something not in a different component of the flow, but you would have to go a long distance around it to somehow intersect that sphere. All right, so this is the separation function. And now the ingredient 2 is that at good points, if we apply the heat operator to the log of the separation function, then this is non-negative. Okay? So the log of the separation function is somehow a super solution to the heat equation on the surface. And this is just a computation. You can just figure it out. Okay? Any questions to this? Okay, so now let me show you how we can assemble these two ingredients. And let me, as a toy case, consider this potential counterexample from before. So again, think of this as being two spheres that are very close together, and they're connected by a little catenoidal neck. So now I'm worried that these two spheres, that they will get come very close together as we're kind of zooming into the flow. And then as we zoom into the flow, they will somehow, will just converge to a double density two sphere. All right, so now let me call R cat the scale of the catenoid, some of the size of the neck between this, so something like this. So I'm worried that R cat goes to 0 and the distance between the two sheets goes to 0. Now, let me also choose a cutoff function. I'll use this in a moment, which basically localizes this catenoidal neck. Okay, so the cutoff function should be 1 near the catenoid at some like scale R times R cat, and then equal to 0 everywhere else, wherever wherever the surface looks like two sheets, and then it should have the obvious bound on the derivative. All right, so now let me put this all together. What I want to now look at is the average separation, the average log separation, where I integrate against kind of the weight being the ambient Gaussian. So I want to look at this integral, and I want to take the time derivative of this quantity. And in theory, this is a really good term. If I hit it with a time derivative, you'll see in a moment, you'll get the right sign, and in theory, you could prove the multiplicity one conjecture using this term. The only issue here is that we would have to use the ingredient number 2 at points, we can only use that ingredient number 2 at points that are good. And points near the catenoid are not good, because near the catenoid, I don't see this behavior of two sheets. So near the catenoid, in some philosophical sense, the separation function is somehow the wrong choice. Maybe somebody can come up with a better separation function. But we somehow can't use the separation function near the catenoid. So instead, I'm going to modify this formula and use this cutoff function to just say, well, we're measuring log of the separation function away from the catenoid and log of the scale of the catenoid near the catenoid. Okay, so this is just is going to differ by a constant, the factor how we're kind of choosing the ambiguity and the factor of how we're choosing the scale. All right, so now I can take the time derivative of this this quantity, and this is a standard formula. It's just Green's formula, or I don't know, integration by parts. I don't know what it's called. And so now, if I hit the Laplacian, if I hit the heat operator, if I hit this log s with the heat operator, I'll get the right sign. And also, if I hit the conjugate heat operator onto this row, then I also get the right sign. The only issue is that, this cutoff function creates some issues. But now you do a few integration by parts, and you just get a small error term that's like located in the annulus near the catenoid, and you can estimate how big the error term is. And if you do this, you'll get that if you just choose your constants right, you can make this error term very small, a very small number divided by tau. Okay. So now if you integrate this, then you get that the average log separation, modulo this like cutoff function, but it shouldn't make a big difference, is bounded from below by 0.1 times log tau minus some constant. However, we've assumed that this picture kind of shrinks to a point if we rescale by a factor of square root of tau. Okay? And so therefore, the separation here at most points is always going to be much smaller than square root of tau. So just by assuming that we converge to a higher multiplicity tangent flow, we have to have an average log separation which is much smaller than log tau. Okay? And so for small tau, you get a contradiction. That's some other proof. All right, so see any questions? So let me just go over the next slide briefly, just to talk briefly about the general case. So what I've shown you here is somehow a nice picture because we know that every region looks like either two sheets or a catenoid. But in general, there could be more than two sheets, and two sheets somehow could cancel, and maybe it may not be possible to always describe the geometry via either sheets or minimal surfaces. So we may see some Grim Reapers or some other kind of regions of different geometry. So now the key estimate, which I'll just project here briefly, is that we're using somehow to get around this issue is the following. So first of all, let me define the local scale as somehow the maximal radius such that a ball, just that the flow within this ball kind of is sufficiently controlled. This is a standard definition. So this is basically a substitute for like the, it's a substitute kind of for looking at the second fundamental form. And let me now define M epsilon to be the set of points in M where kind of locally the flow looks either like a minimal surface or like kind of like several sheets or something of this type. So in the previous example, M epsilon was everything, and therefore kind of this toy case worked out so well. But if M epsilon is not everything, then we prove this estimate, which says that if we integrate r log to the power of -2 over the complement of the set, so over the set of points where the geometry may be described by surfaces that are not minimal surfaces or not two sheets, then this set is somehow very small in the sense that it's so small that it somehow can be bounded by the drop in Gaussian area between two scales. And so therefore, kind of that set where maybe more complicated geometry may happen, like that can't be described by minimal surfaces or sheets, is so small that somehow it doesn't contribute much to the error on the right-hand side. Okay, so maybe I'll stop here. Sorry for going over time. Thanks.
Okay, questions for Richard?
So this separating function is was some known case before, or it's just the first time you and found it? It seems to play a quite crucial role here.
Yeah, that's a crucial one. I'm not aware. I think it's probably new as far as I can tell. Yeah. So
Is that also such a function can be also introduced in more general cases like 5 dimensions? So it probably doesn't matter. It's any dimension, I guess.
Yeah. Actually, like in most of these ingredients hold in higher dimensions. There are only very few things that don't work out in higher dimensions. But yeah, the separation function holds in higher dimensions. I think there may also be applications for just minimal surfaces. Yeah.
Because people are still digesting. Okay, so
So the multiplicity one conjecture. Okay. So the conjecture was, I think it was proved by Bin Wang and Hao Zhao Li in a special case, right? For type 1.
Wait, sorry, it's hard to hear.
Multiplicity one conjecture was proven
By Bin Wang,
special cases?
yeah.
Is
there
I don't
anybody-
know the literature. I mean, I'm sure there might be some cases where it's proven.
Yeah,
but-
the type 1 case.
Oh, in the type 1 case, yeah.
So can you say something about the difference?
Or mean convex, in the mean convex case, yeah. Yeah, I don't know much about, I don't know the whole literature so in the mean convex case, you can use this inscribed radius estimate like that. So 1 over the inscribed radius satisfies this same PDI as the mean curvature. So you can just bound 1 over the inscribed radius or kind of 1 over the injectivity radius and the normal injectivity radius by the mean curvature. And somehow this estimate for 1 over the inscribed radius like this is quite subtle. I mean, it's the computation for the separation function is much simpler. Maybe this has somehow, I mean, this confused me for a while. I wanted to use the inscribed radius for a long time, but yeah, but I don't know much about the previous work other than the mean convex one.
Thanks.
Well, there's no questions, no further questions. Let's thank Richard again.